welcome to our first video on projectiles. One of the weird things that we run into is when we start moving in 2 dimensions, it's a lot harder to start thinking about it. One of the first things we often talk about is I roll a ball off the table, right? I roll a ball off the table, or I knock it off the table like demonstrations or in videos. How far it goes depends on how fast it leaves the table. It could barely fall off the table and go like so. It could be given a little shove and go like so. Or if you really, really send it flying, it goes like so. In all three cases, the motion is parabolic. There's an acceleration. But that acceleration only occurs in the y direction. Another way to say this, the velocity in the x motion doesn't change. And the time it falls for doesn't change. That's entirely dependent on the height. No matter how you shove the object off, it still will land in the same amount of time. That's what the lessons and videos and demonstrations show us. But it's hard to internalize. You want to say, well, it's moving faster off the table, it's going to be in the air longer. But this ball that was barely shoved, and this ball in red, and this ball in blue, would all hit in the same amount of time. And this is hard to understand. It just doesn't seem to make sense, no matter how many demonstrations we see, observations, but it's true. Now, because this is all the same, all this time, what determines how far it goes, how far it lands away? Well, that's entirely dependent on how fast it was going when it leaves the table. This leads to a conclusion, and what that conclusion is that motion in the x direction and motion in the y direction are independent. Moving in the x direction doesn't affect the y, and moving in the y doesn't affect the x.
Now, to many people, this doesn't make sense right off the bat, so allow me to provide this analogy.
Imagine you're on a football field. Let's say you're running this way. Running faster this way doesn't make you fall up and down. Running faster this way doesn't take it longer to fall. Now, let's take a look at a few problems, some ideas of how this can work. Now, typically when I work a problem, I like starting from one end and working what typically is considered forward. How far will this go, given these information and all that? But today we're going to start by working backwards. This is for two reasons. Number one, it is a far more common experiment you'll see in the lab to measure the distance it went to figure out how fast it was going originally. Because it's hard to measure speed, but it's easy to measure distance. And number two, we're going to have to do both anyway, so we might as well start with the one that's a little more familiar, a little more accessible. So in this problem, you're going to roll a ball off the table. What I ultimately want to know is how fast was that ball rolling before it left the table based on the information we see here. Now, here's the trick. Here's the rub. The only thing that we know for sure is that it's moving in the x and y direction. Now, it's moving through both. Because x and y motion are independent of each other, we can treat this as two separate problems. We're going to do the y calculations in red and the x calculations
In black.
The same process is true either way. But let's take a look at how this works. So if the ball is rolling off the table, it's rolling along the table like this. It's heading this way originally. What do we know about that for sure? I like to start there to think about it. Well, it has some velocity in the x direction, so we're going to put our x values here. It has some velocity, but we don't know what it is. That once it's in the air, there's going to be no acceleration. There's going to be no change in the x velocity. This is one of the fundamental assumptions we make about every projectile problem. Once an object is in the air, the x velocity does not change. This works on the micro scale. When we start getting to larger scale where we have to talk about air and wind resistance, it becomes a problem. But those make such small changes on the scales that we're going to be working on, or most of the world operates on, that it doesn't matter. They're small deviations. We're talking on this course of 200 meters, maybe half a meter difference. While these are not exactly truths, they are very convenient lies and very good approximations. Disclaimer aside. So my v is going to equal my v naught for this entire flight through the air. And my acceleration is going to equal 0. I know how far I went. My change in x values are 3.3 meters. But I have 2 unknowns and 2 givens. I can't solve for my velocity. If I wanted to solve for this, I need either my initial velocity or my final velocity, which would solve the problem because they're going to be equal to each other because my acceleration is 0, or I need my time. But I don't know that either. And that's a problem. So let's go take a look at the y and see what we can do there. My y givens are very similar. I know how far it goes in the y. It's going to be 1.5 meters negative. Y negative, I'm going to say that this is 0 and it's falling down.
Falling from 0 to a lower point would give us a negative displacement. Final minus initial, negative value minus 0 gives you negative.
Delta y, negative 1.5 meters. When you measure a table, you measure from the ground up. When you're measuring the fall, you measure from the start point down, is another way to think about this. We know the acceleration. It's in free fall. It's falling. Acceleration due to gravity is always 9.8. In this case, negative, because we're going to call up positive, down negative. We also know the initial velocity in 0. If it's rolling along the table like this, it's only moving in the x direction. Much like the football player, they're only moving this way. My initial x velocity is 0. And because of this potential confusion, what a lot of people will do, and what I recommend you do, is label these with x's and y's. So instead of saying v naught, we're going to say v naught y. Instead of saying a, we're going to say a y. And the same thing for the x's. We're going to say vx, v naught x, ax, but not t. The one truth for this is that time moves on uncaring about whether or not an object's moving or how it's moving. The time at which this ball hits the ground is the same time as it hits in the x direction and the y direction. The time between these two is the same. That is the second assumption we make about projectile motion. So if we can find the time here, it'll be the same time here, and then we can use that to solve for our velocity. Let's put those assumptions I'm making about projectile motion up here in blue. Main assumption we make about projectile motion is that the only cause of acceleration is gravity pulling down. No other sources of acceleration, which means we're ignoring friction, we're ignoring the air. And yes, that introduces some small amounts of air, but again, small amounts. The consequences of this, acceleration in the x direction is 0. Acceleration in the y direction is 9.8. Could be positive or negative depending on which way you define. Typically, we'll say negative, but that is flexible. Also, your v initial x and your v final x are going to be the same. These are assumptions we make to simplify it. Combine these with the facts that the x motion doesn't affect the y motion, at least on the scale we deal with, and that the time is the same between the two of them. It doesn't take longer or a different amount of time to fall in the x direction does than y. It's hitting at 3 seconds or however long it is, both cases. And these problems become a lot easier to solve. So how do we go? Well, once we know the time that it falls in, how long it takes to hit the ground in the y direction, which will be the same if we dropped it from 1.5 meters or had it roll off at going 1,000 miles per hour, or we shot it from a gun, it's still going to hit the ground at the same time because the drop only depends on the y. Once we have that t, we can plug it in here and solve for my v. So let's go ahead and solve for t. In this case, I have delta y, a, v naught, and t. Instead of saying delta x, we just say delta y. It's the same equation, same idea, just different variable. Equation that ties all this together delta y equals v naught t plus 1/2 a t squared. Oh no, we might have to do a quadratic, except v naught y is 0. Start simple. Negative 1.5 equals 0 plus negative 4.9 t squared. I'm not solving this one symbolically because we've done that a few dozen times, and I want to make the point that you can do this without the quadratic. If you were to solve this symbolically, it would look something like that. Once you plug in and solve, you get that t equals, grab a handy dandy calculator, you'll get a positive and a negative, but does the negative number make sense? And it doesn't. 0.55 seconds. Now that I have this time here is the same as this time here. So I can come over here. And now I can solve for my initial or my v final x. Now, there are several equations available to us. If we find one, we find the other because they're the same. So do keep that in mind. Pick whatever equation's easiest. I'm probably going to pick this one because while it seems the most complicated, my acceleration is 0, which means that cancels out. And in this case, v naught x simply means delta x over t, which means that it's going to be 6.05 meters per second. And there we go. From this, we can go back and measure and predict and find how things are going. If you're in the classroom with a meter stick, go ahead and give this a try. If not, you can do it at home, but follow the math through. Now, we've done it one way. Let's do it the other way. On the board here, I've set up a new situation. I've changed it around a little bit to be a little fresher. First things first, the height of the table is only 1 meter. Secondly, the initial velocity here is 1.37 meters per second. Find how far it'll land from the table. Predict it. How are you going to do this? Well, first things first, you need to figure out how long it takes to fall. Once you figure out how long it takes to fall, then we need to talk about how far it goes. Go ahead, give it a try, check back after the pause. Okay, let's break this down. First thing I did is I went through the y side of the equation. Negative 1 meter, velocity initial 0 because it's not going up or down. The acceleration in the y direction is 9.8. Negative, and the time is unknown. Solve for t, get 0.45. Take that over to the x side, and get my delta x of 0.62 meters. There you go. Have a good one.